So in this video, we will be talking about asymptotes. Okay. Now, before we get to that and explain to you what asymptote is all about, there are a few basics that you need to know. So let us discuss them first real quick. The basics are that when you have a function f of x, okay, it can be any function, but then when we usually plot a function, the f of x is usually equal to y. So f of x is written on the y-axis. That's a convention. And this horizontal axis is x. Okay. Now I have taken two sample functions over here. One function is over here. This is my one function f of x. Now asymptote is basically that asymptote can be this line. Okay, this line here is called as a vertical asymptote. Now what this simply means is this function will ever extend on this side. Okay, and it will get close to this line, but it will never meet this line. And that is basically nothing but an asymptote. And I can call this line as a vertical asymptote. The same goes here, that maybe this type of a function will extend on this side, but it will never meet this line. Okay, so this line is called as a horizontal asymptote of this function. Now in case of this function has got a slant asymptote. So it's neither vertical nor horizontal, but it is of this shape, and this is called as a slant asymptote of this function. Okay. Now in case I'll give you some examples to explain to you how this asymptote works. So let us begin with the first example. Supposing if I have, say, a function f of x, okay, that is x square plus, say, 3x plus 2 divided by x square plus x minus 2. Okay, if this is the function, of course I can find, these are the quadratic equation. I can always find the roots of this function and write it in this form as well. It is exactly same as, this will be x plus 1, x plus 2. Those are the roots of numerator. And for denominator, the roots are going to be x minus 1 and x plus 2, right? So you can write it in the roots form like this. Anyways, now if this is the function f of x, please note that f of x is nothing but equal to y, right? So I can write this as y as well. Now, what do you mean by a horizontal asymptote? Now let us try and understand this thing better. That when I say a horizontal asymptote, okay, usually it is denoted by a dotted line. Okay, the horizontal asymptote is a line with the equation y is equal to a. I hope you get that. A line parallel to x-axis, a horizontal line, will have equation y equal to a, where a is this height. Okay, I hope you understand this part. Now, how do you find a horizontal asymptote? Now, for, say, horizontal asymptote, okay, this is going to be that when x becomes infinity, okay, this line just extends like this. Okay, as x grows more and more, this is the x axis, right? As this grows on this side, okay, the function will also become infinity. Okay, so we want to find out the equation of this line. So we can use a limit over here to find out the horizontal asymptote. We usually write like this: f of x is equal to, we can apply a limit to this. This is a limiting case when x is infinity. Look, you can't put x infinity, because if you put x infinity in this function, the answer will straight become infinity. So you can't do that. Let us put limit of x tends to infinity on this function. Okay, just see how I simplify this. This is going to be x square plus 3x plus 2, and this is x square plus x minus 2. Now divide the numerator by x square and denominator is also by x square, assuming that x is not 0. So when I divide like this, it is going to be limit x tends to infinity. And when I divide by x square, it will be 1 plus 3. Now when I divide by x square here, this will be 1 by x, and this will become 2 by x square. Now do that same thing in denominator as well. Divide here as well. This will be 1 plus, this will be 1 by x. 1x will cancel out. And the next one will be minus 2 by x square. And now at this point of time, you can simply evaluate this limit and put x is equal to infinity. When you do that, you will get this as 1. The 1 will stay as it is, but then this will become 1 by infinity. And 1 divided by infinity is 0. This term is 0. This is also 1 by infinity. So 1 over infinity is going to be 0 as well. So this is 0. And then same goes here. This is 1 plus 0 minus 0. I hope you get the point that I got 1 over 1. It is just 1. Okay. And now that I got f of x at limiting value x tends to infinity, I got this is equal to 1. So can I say at x tending to infinity, the value of f of x at x tending to infinity, the value of f of x that I got is equal to 1. And when basically I say x tends to infinity, okay, now that is basically my horizontal asymptote. And please note that f of x is nothing but y. I've already written over here that f of x is nothing but y. That's the vertical axis. So this implies y is equal to 1. And this is the final answer that I've got for a horizontal asymptote. Okay, I hope you got the solving part. So for the first example, I have already found out the horizontal asymptote, and this is the procedure to do that same thing. Now let's go for a vertical asymptote, and let us try and understand how do we find vertical asymptote. For vertical asymptote, when you want to find out, okay, the function f of x that I have is nothing but x plus 1, x plus 2. I'm writing down the factor form, which is this function over here is written like this. And this is x minus 1 and x plus 2. Okay. Now you have to understand one step over here that in the numerator, okay, I am dividing by x plus 2. And in the denominator also I'm dividing by x plus 2. So dividing numerator, denominator both by x plus 2. If I do this step, okay, this step always comes with the condition that x plus 2 should not be 0, because we never divide by 0, right? So this step comes with the condition that when you're dividing by x plus 2, your x plus 2 should not be 0. Okay. Now once I do that, do you see the x plus 2 of this will cancel out? Both the numerator, this will cancel out, and this will also cancel out. So only so much function remains. So I'll write down f of x is equal to x plus 1 upon x minus 1, but with a condition that x plus 2 should not be 0, or I can say x should not be minus 2. Now that is the condition for this simplified version of this function f of x. So we also say that minus 2 is a removable discontinuity. It is a discontinuity of the function, but it can be removed. All right. Now, once you do that, the next we want to find out is a vertical asymptote. So for vertical asymptote, please clearly understand that when x becomes 1, okay, the value of, now understand this f of x is nothing but y. Okay, can I say y is equal to x plus 1, x minus 1. Okay, so now the discontinuity here is x minus 1, that is x is equal to 1. So for vertical asymptote, the equation is x is equal to 1. Okay, now that's going to be the equation of vertical asymptote. So this one over here, the vertical asymptote will have, this is a vertical line, right? And the vertical line equation is going to be x equal to something, and that is x is equal to 1. This is how we got it. So for given function, I have found out, now we look at this function here, for this f of x, okay, we have found out the horizontal asymptote to be y is equal to 1, and vertical asymptote to be x is equal to 1. Okay, that is the method of finding vertical and horizontal asymptote. Now we will see one more question, and there we'll deal with the slant asymptote. So I'll take an example for that also, and we will solve the question. Now consider the next question over here, and we have a function f of x given to us. We can write this very well as equal to y, and we have to find out a slant or a oblique asymptote. Oblique asymptote is going to be this line like this. So how do you solve this? Now, first point that you have to make a note of is for slant asymptote, we must have a function where degree of numerator is 1 greater than degree of denominator. So what you basically need is you want the degree of numerator. Do you see it is over here? It is 3. Should be 1 greater than degree of denominator. The degree of denominator is 2 and degree of numerator is 1. Now when this condition is fulfilled, you will definitely have a slant asymptote over here. And to find that slant asymptote, you basically do the division. Look, your f of x. I'm going to write down this f of x as y now. So this f of x, I write it as y, and then y is equal to x cube plus 1 divided by x square plus 1. Now in this case, we'll do the actual long division. So let me do the division here. X cube plus 1 divided by x square plus 1. So once I do that, first for the long division, the first term I'll write down is x. Okay. Now you cross multiply here. This will be x cube, x times x square, plus x times 1 is going to be x. And now let us subtract this. This will become negative. Negative. This x cube and minus x cube becomes 0. And this will be 1 minus x. So I got this as 1 minus x. Now this is the remainder. Okay. As soon as you get to this level, you stop solving. And now this very division, okay, can be written as, so let me write that down. So I'll get y is equal to, the quotient here is x, plus the remainder is 1 minus x divided by x squared plus 1. Once you get it in this form, this part here is going to be the equation of asymptote. So from here, I will say equation of slant asymptote is going to be y is equal to x. Now, how will that look like? Y equal to x is a 45-degree line, right? So this is x-axis, this is y-axis, and y equal to x is a 45-degree line, and that is my asymptote. Simply means that my function will have, you know, an asymptote like this. This is the function, okay? And it will have this slant asymptote whose equation is going to be y is equal to x. So this is basically the technique of finding slant or oblique asymptote. And I hope you followed how this works.